Welcome to another Mathologer video. You all know those two freaky identities over there, right? For most people they are just that, pretty freaks without any deeper meaning. Unless of course you're a Mathologer regular, because if you are, you would have found out in two earlier videos that these two identities and their underlying equations, those two there, lead very interesting secret lives. Heron's formula, the heptagon golden ratio and all that jazz. If you've not done so already, definitely check out those two earlier videos for a lot of amazing and beautiful maths. Anyway, what even most Mathologer regulars won't know is that these two identities up there are just the start of a very interesting infinite sequence of similar identities. Really? Yes. And in fact, there's a whole world of sum equals product monsters out there. Let's go and explore. Okay, infinite sequence. So what's next? Well, obviously the next equation at the bottom is this one here. X plus y plus z plus u equals x times y times z times u. And at the top we are looking for a solution of this new equation in positive integers. So to start with, we want 4 positive integers on both sides of the equal sign at the top. Can we spot a pattern? Well, if we shuffle things around like this, as I did in the thumbnail of this video, things are starting to look pretty symmetrical. Okay, bad one. 2, 3, what comes next? 4, of course. Then 2, 2, what's next? Another 2 maybe. Now, 1, what's next? Well, let's first add and multiply what we've got so far. 2 plus 4, that's 6. 4 times 2, that's 8. Now, if you'd have to bet your life on what number comes after 1 in this setup, you'd probably go for 1, right? Okay, so let's try 1. On the right, multiply by 1. The product actually doesn't change. Aha! Can you see what's happening here? Okay. On the other hand, adding the corresponding one on the left ups the sum by 1. 7 and 8 almost equal. Obvious how to finish, right? Just chuck in another 1. 1 on the right, nothing changes. Add 1 on the left, ta-da! Equality. What's next? Well, after 4 comes 5, so replace 4 by 5. That makes the sum on the left go up by 1. On the right, replacing 4 by 5 ups the product by 2. And now we know what to do next. Just pad with another 1. And it's clear sailing from here, forever and ever after. 2, 3, 4, 5, 6 and so on in the middle. Then 2, 2, 2, 2, 2 and so on. And pad out the rest with 1s, such that in every identity the number of terms on the left and right is equal to the largest number in the middle. There. 3 terms and 3 in the middle. 4 terms and 4 in the middle, and so on. 2 remarks. 1, the whole padding with 1s business may come across a little bit like cheating. But if you want to play this game with positive integers, you really don't have a choice, because if you also insist on not involving any 1s, then 2 plus 2 equals 2 times 2 is the only identity that works. Second remark. Taking this padding with 1s idea one step further, it's clear that there are many more of these sum equals product identities. To start with, a random assortment of positive integers, say 2, 5, 7, doesn't matter which. You can even have some numbers repeat, like for example start with the numbers 2, 5, 5, 7. Calculate their sum and product. Then, as in this example, in general, the product will be greater than the sum. Subtract the sum from the product. Then, if you pad out the left and right sides with that difference number of 1s, you get one of our identities. So in this case, add 331 1s to the left and multiply the same number of 1s on the right, and you get equality. Super easy. In fact, the first time I stumbled across all this, I thought, cute, but in the end, pretty trivial, right? But let's slow down. After all, even if something is easy to understand, it may still lead to deep and beautiful mathematics. Right? You can explain to a 10-year-old what a prime number is, but at the same time, some of the greatest mathematical theorems and some of the most important and hardest problems are about prime numbers. As the Mount Everest example, the Riemann hypothesis is all about primes. And it turns out that the world of sum equals product identities is also full of pretty surprising prime number marvels and mysteries. Maybe not the Riemann hypothesis, but still great stuff. In the rest of this video, I'd like to tell you about one particularly nice mathematical marvel involving the mysterious Sophie Germain primes. These were discovered 200 years ago by, you guessed it, the mathematician Sophie Germain. She discovered these primes while working on Fermat's last theorem, one of the most famous open mathematical problems at the time. But before I get started, I'd like to take this opportunity to pick all your brains to dig for mathematical treasure. In your mathematical journeys, did you ever encounter any of these sum equals product identities or equations in surprising settings or contexts? For example, my friend Marty recently told me about this paper by Stanford mathematician Brian White in Inventiones Mathematicae, one of the most prestigious maths journals. Turns out that amidst a lot of very high-powered mathematics, 2 plus 2 equals 2 times 2 ends up being the ingredient that makes everything come together. Really quite wonderful. Anyway, if you know of anything like this for any of the sum equals product identities and equations, please let the rest of us know in the comments. Okay, now let's have a close look at the world of sum equals product identities. Let's call the number of terms on one side of a sum equals product identity the length of the identity. So 2 plus 2 equals 2 times 2 has length 2, and 1 plus 2 plus 3 equals 3 times 2 times 1 has length 3. It's the natural to ask how many sum equals product identities there are of a given length. Well, it's natural for us mathematicians to ask this. It's what we do. So here, straight away, a plot of these numbers of identities up to length 10,000, taken from a really nice paper by the Polish mathematician Zakarczemny that I linked to in the description of this video. What a weird looking plot. Definitely not the nice curve that you may be expecting to see here, but a standard plot regardless, consisting of one dot each for the possible lengths between the smallest length 2 and length 10,000, right? Take any length, then the height of the dot above it is the number of sum equals product identities of that length. In this case, around 25. Clearly, the dots are all over the place, meaning that the number of sum equals product identities for different lengths are all over the place. The general trend is logarithmic growth, but the trend is not very trendy, is it? As we increase the length, we come across larger and larger numbers of identities, but at the same time, really small numbers keep popping up. Let's have a closer look at what happens for the smallest length. All right, we know that for every length there is one of our basic sum equals product identities over there. In fact, for length 2, there's only this one sum equals product identity. That is, the equation x plus y equals y times x only has one solution in positive integers. The same is true for the next equation. The only solution, up to shuffling the terms, corresponds to our second basic sum equals product identity. Same for length 4. Then 5. But now it turns out that for length 5, we also have this second sum equals product identity. And also this one here. But then that's it. For length 5, there is a total of 3 identities. Those 3. And now we've got going, there should be lots of identities of length 6, right? Nope, for length 6, there's just one again. And after this, things continue up to length 9 as follows. Here are 2 little challenges for you. First, can you find all the identities of length 10? Also, can you find a length for which there are more than 10 identities? Leave your answers in the comments. Okay, so what's a natural question to ask here? Who cares? No. Natural or not, that question is taboo around here. Seriously, what might we ask about these lengths? Well, how about for which length is there only one sum equals product identity? The basic identity is the only one, right? Natural question. Well, so far we've seen 4 such lengths. 2, 3, 4 and 6. Are there more? Yep, 24. It turns out there's also only the one sum equals product identity of length 24. And then we also have 114, 174, and 444. What's next? Should I leave you to hunt for the next one? Maybe not. In fact, mathematicians have used computers to check all lengths up to 10 billion and have not discovered another length with only the basic solution. So maybe that's it. And the list ends with 444. But we don't know. Checking all the way to 10 billion is very suggestive, but 10 billion is still a long, long way from infinity. Now, how could we settle this question? Well, we could leave the computer running, but that will take an infinite amount of time, and we're probably a little bit too impatient for that. So instead, how might we think our way to a solution? Well, a good starting point would be to figure out what all these special lengths have in common, right? Okay, so have a look at those numbers up there. Is there any pattern, any common trait that sticks out to you? Lots of 4s, yes, but sadly that's not it. Now, I could just tell you the surprising answer, but that's not the Mathologer way. Instead, I will do what I often do. I'll kidnap you and take you on a journey of discovery, which leads naturally to this answer. Let me know in the comments whether you enjoyed being kidnapped. Okay, let's start with something easy. Let's figure out why, for length 2, there's only one positive integer solution of this equation, namely 2 plus 2 equals 2 times 2. How would you get started on this mission? Easy. Solve for one of the variables, say y and hope for the best, right? Okay, so algebra autopilot on. Okay, shuffle this one to the other side, great. Okay, take that one out. Okay, just one y left and it would now be very easy to finish solving for y. However, at this point, an experienced algebra torturer may notice something else, an opportunity to simultaneously isolate both variables. Have a look. Take -1 on the right and add 1 to cancel out the -1, right? -1 plus 1 cancels out to 0, so nothing's changed. Except, can you see it? There. Shuffle to the other side and take that out. That's nice, isn't it? We managed to rewrite our initial equation in a second supersymmetric way. In particular, this means that both equations have exactly the same solutions. And so, what are those solutions? Well, easy. Since x and y are supposed to be integers, so are the numbers x minus 1 and y minus 1. But then, what this says is that the product of the orange integer and the green integer equals 1. Of course, this means that either both orange and green are equal to 1, or both are equal to -1, right? 1 times 1 is 1, and -1 times -1 is also 1, and that's all. Now, if both numbers are equal to 1, then, well, what? X minus 1 is 1, so x is 2, and so is y. That's our 2 plus 2 equals 2 times 2 solution. On the other hand, if both orange and green are -1, then we have x minus 1 is -1, and so x is equal to 0, and so is y. 0 plus 0 equals 0 times 0. That's also correct, but we've decided, well, rather, I made an executive decision for all of us that we'd only be interested in solutions with positive integers. All right, that was definitely a slick way to show that we have only one solution for length 2. But more importantly, all this mucking around leaves us just one step short of another crucial insight. Okay, again, this nicely symmetric equation is equivalent to our initial sum equals product equation. But here's another trick. Just shuffling everything in the bottom equation to the left of the equal sign, we obtain a third equivalent equation. Does this quantity on the left ring a bell? That difference between a product and a sum? Right? If you start with two positive integers x and y, then this difference tells you how many ones you need to pad these two numbers with to get one of our identities. In the case of x and y, both being equal to 2, this difference is 0. But now let's consider any old x and y, and the difference between the product and the sum is some other number. Let's call it d. then the exact same algebraic acrobatics as earlier gives us this equivalent equation at the top. Easy for you to nut out the details, and of course you should. No freeloading here. Anyway, let's check using an example. X is equal to 2 and y is equal to 7. What's that difference? 2 times 7, that's 14, minus 2 plus 7, 9. 14 minus 9 is 5. Okay, that means we need to pad 2 and 7 with 5 ones. And actually, if we do that, we just get one of our basic identities, that one here. Now, what about the top? X minus 1, that's 2 minus 1. 2 minus 1 is 1. And y minus 1, that's 7 minus 1, that's 6. 1 times 6 is 6. Works. That 6 is the difference 5 from before plus 1. 5 plus 1 is 6. Now, here comes the nifty bit. 6 is also 2 times 3. But then, if x minus 1 is 2, then x is 3. And if y minus 1 is 3, then y is 4. But now we can use these new x and y to get another difference of 5 at the bottom. 3 times 4 is 12, minus 3 plus 4, 7. 12 minus 7 equals 5. But now that means that if we pad out 3 and 4 with 5 ones, we obtain a second sum equals product identity of exactly the same length as the basic identity we started with. Can you see where I'm going with this? Well, what we've just discovered boils down to a nice way of creating new sum equals product identities from our basic ones of the same length. That's important. Let me spell out this streamlined way of creating new sum equals product identities using a couple of examples. Okay, well, let's start with the basic sum equals product identity that we just encountered. 2 and 7 padded out with 5 ones. All right, 7 minus 1, that's the 6. 6 was 2 times 3, okay. Then 2 plus 1 is 3, and 3 plus 1 is 4. And that's our new sum equals product identity of length 7 once again. Now, let's start with the basic identity of length 5. 5 minus 1 is 4. 4 is 2 times 2. 2 plus 1 is 3. And there is the new sum equals product identity of the same length as the basic one we started with. Does this always work? Well, here is what quite a few will already be waiting for by now. 6 minus 1 is 5, but now 5 is prime. And so the only way to write 5 as a product of positive integers is 1 times 5. Adding 1 to both 1 and 5 gives 2 and 6, which after padding with 1s only gets us back to where we started from. In general, for a given length n, our construction will give no new sum equals product identities if n minus 1 is a prime number, and at least one new sum equals product identity if n minus 1 is not a prime number. And that tells us something very interesting about our puzzle. Remember, our puzzle was to try to determine, without using a computer for infinite hours, for which special length n there exists just one basic sum equals product identity. And this is what we just discovered. Any of those special numbers minus 1 must be a prime number. How neat is that? Let's check. Those are the known special lengths, all minus 1. 1, 2, 3, 5, 23, etc. works. Those are all prime numbers. Well, that 1, the first of the numbers, that's not a prime, but close enough, right? 1 used to be a prime, and it is at least still an honorary prime. Nothing goes into it except 1 in itself, which is what matters here. Anyway, what we've discovered is that if there is another one of those special lengths, does not matter how large, then that special length minus 1 must be a prime number. So we only need to look for special lengths among those numbers that diminish by 1 are prime numbers. That's all definitely some pretty prime number action there. Okay, but still, there are a lot of prime numbers, and so there must be something extra special about those particular primes up there. To track down that extra speciality, let's have another close look at our lineup of small cases. All clear so far? Great. Again, over there is our list of small cases. What I've highlighted in this list are the first three in the infinite family of special identities that our streamlined way of making new sum equals product identities from the basic one produces. Remember, this infinite family and the streamlined way of producing it resulted in our neat prime number inside. Another close look at our list of small cases yields a second infinite family of identities. This second infinite family and the rule underlying it will lead us to another really neat prime insight about our special lengths. Ready for this? Okay, let's go. All right, here are the first two identities in our second family. What's the rule here? How do you go from length 5 at the top to 2 to 2 in the yellow box, or from length 8 to 2 to 3 in the blue box? Well, we've not got much to work with so far, so let me also show you the next couple of identities in this family. 2 to 2, 2 to 3, 2 to 4, so we're all guessing that 2 to 5 is next, right? Well, let's see. 2 to 3, not 2 to 5. In fact, if you look at a couple more examples, the only obvious pattern is the fact that we always get a 2 and something else. But since that one 2 is common to all the new identities, maybe the better question to ask is, how does the 5 turn into 2, 2? And how does the 8 turn into 2, 3? Well, actually, it's not hard to figure out what the general rule is, now that we know what we're gunning for. Right? Start with some n. We want to find x and y up there, such that both sum equals product identities have length n. And how do we do that? Easy. Do some algebra torturing. First, the number of ones in the basic sum equals product identity at the top is what? Well, the length is n, and only the 2 and the n are not ones. And so there are n minus 2 ones, right? On the other hand, the number of ones in the second sum equals product identity is, as usual, the product of 2x and y minus the sum of 2x and y. Next insight. There's one more 1 in the first identity than in the second. Have a look. One more 1 at the top. So adding 1 to the second expression makes both expressions equal. Now, simplifying on autopilot and isolating the x and y as previously, recast this equation in this supersymmetric form. At this stage, the algebra involved should be a piece of cake for you, and so I won't bother with the details. But one of you should definitely do this in the description, in the comments. For comparison, the corresponding equation for our first rule is this. So exactly the same, except for the 2's. Now remember, the first equation translates into this rule for generating new special sum equals product identities. Subtract 1 from n, write n minus 1 as a product, add 1 to both factors to get the new x and y. Similarly, for our new second rule, we multiply n by 2 and then minus 1, write 2n minus 1 as a product, and finally add 1 to each factor and divide by 2 to get the new x and y, right? And here is the new rule in practice. 2 times n minus 1. So 2 times 5 is 10 minus 1 is 9. Write as a product, 9 is 3 times 3. Add 1 to each factor and then divide by 2. 3 plus 1 is 4, divided by 2 is 2. Throw in that common 2. Et voila! Here is our new special sum equals product identity, exactly as long as the basic one we started with. Another example. 2 times 6 is 12, minus 1 is 11. Prime number, and we're stuck. Next. 2 times 7 is 14, minus 1 is 13. Stuck again. But now, 2 times 8 is 16, minus 1 is 15. Aha! 3 times 5, plus 1 divided by 2, both of them. 3 plus 1 is 4, divided by 2 is 2, and 5 plus 1 is 6, divided by 2 is 3. 2, 3. Join in the common 2 in front, and done. Okay, where does this leave us in terms of characterizing our special lengths? Well, we already know that if n is a special length, then n minus 1 must be prime. But now, with our new rule, we also know that in addition twice n minus 1 is prime as well, right? There, all those new numbers, 3, 5, 7, 11, 47, etc. are also prime. And so if we ever find another one of those special lengths, just times it by 2 and then minus 1, and you get another prime. Super interesting and surprising, don't you think? Well, it sounds unlikely, doesn't it? What are the chances that both n minus 1 and 2n minus 1 are prime numbers? Or, phrased differently, what are the chances that, given a prime number p, twice p plus 1 is also a prime number? As I already mentioned at the beginning of this video, it was the mathematician Sophie Germain who was the first to ponder this question around 1800 while trying to prove Fermat's last theorem. Because of this, a prime number p such that 2p plus 1 is also prime is now called a Sophie Germain prime. One of Sophie Germain's major claim to fame is that using her primes she was the first to make significant progress towards proving Fermat's last theorem for infinitely many prime exponents. Prior to her research, people only considered individual exponents. If you've not heard of Sophie Germain, definitely check out the remarkable story of her mathematical life. Completely self-taught, had to pretend that she was a man to enter maths competitions, the whole bit. Okay, history lesson done. Back to work. So we know that every special length minus 1 is a Sophie Germain prime, right? What about the other way around? Is every Sophie Germain prime also a special length minus 1? The answer to this question is, sadly, or not sadly, depending what you're cheering for, there are a lot more Sophie Germain primes. As it happens, Sophie Germain primes are nowhere near as rare as one might expect. To illustrate, here are all the Sophie Germain primes up to 113. Computer searchers have produced ridiculously large Sophie Germain primes, which also happen to be useful in cryptography. In fact, the people in the know believe that there may well be infinitely many Sophie Germain primes. Apart from the two special infinite families of sum equals product identities that led to our prime number insights, there are of course many other infinite families one can investigate and milk for further insights into our special lengths. However, nothing quite as neat as what I've talked about today has been discovered. Anyway, check out the linked papers in the description of this video for more details. Okay, what other interesting sum equals product results and questions are there? Let's finish up with that. First off, if I had to bet my life whether or not those numbers up there are the only special lengths, with just one sum equals product identity each, I'd go for yes, those are the only ones. But then, what about the lengths that correspond to exactly two special sum equals product identities? Well, a couple of the small lengths that we considered earlier were of that type. There at the bottom, there are exactly two identities each for lengths 7, 8 and 9. Turns out that the list of known lengths of this type is also fairly short. To be precise, we know 49 such lengths, the largest known being 6,324. There are also some primes hiding in these numbers. Turns out that if there are exactly two special identities of length n, then the number n minus 1 or the number 2n minus 1 or both are prime. For the first 13 in this list, here are the corresponding n minus 1s and 2n minus 1s. And here are the primes among these n minus 1s and 2n minus 1s. That's a pretty cute result too, don't you think? Now, it's possible to show that even if one of these n minus 1s or 2n minus 1s is not a prime, such a non-prime is nevertheless always close to being a prime number in a certain sense. What does it mean to be close to a prime? To find out, check out the details in the description of this video. Now, by now, you'll probably not be surprised to hear that all sum equals product identity experts also suspect that those 49 special lengths are the only ones corresponding to exactly two identities. In fact, it's reasonable to conjecture that for any fixed number of identities, there are only finitely many lengths corresponding to that number. All very intriguing, and lots of open, interesting questions remain to be tackled in this area. Anyway, That's it for today. Don't forget to let the rest of us know of any interesting occurrences of our special identities in the wild. Picking the brains of zillions of people in this respect was one of the main reasons for me to put together this video. I'm really interested in those freaky identities.